Hello and welcome to this lecture in the series of analytical mechanics. The topic of this lecture is variational calculus and its relation to mechanics. The topic of variational calculus has deep roots in pure mathematics, so it's very natural that you feel strange, especially for beginners, why to study variational calculus while you are studying mechanics. So to provide some motivation for studying this topic, I would like to speak about this real story, which occurred in the 17th century, and the persons involved in this story are very well known scientists. So it began when John Bernoulli in 1696, at the end of the 17th century, he issued a new problem. You can find more details about the history of this of the problem issued by John Bernoulli in this book, in this source book in mathematics by Smith and David Eugene. Anyhow, in 1696, the challenge was made public by John Bernoulli. So what's the challenge now? The challenge, which is written in these words now, is that the following: we are given 2 points. So we are not searching for the 2 points AB, but we are given the coordinates of 2 points AB. However, both points lie in a vertical plane. Let us say their plane is the plane of the screen in front of you or the paper, but it's a vertical plane. We now need to assign a mobile particle. This particle can be a ring or a bead. But it's sliding frictionless on some path A and B, along which it will be descending under its own weight. However, this path is unknown. The path of the particle is unknown. Okay, we want to find the path A and B such that the particle passes from point A to point B in the briefest time. So let us try to provide some more explanation about this problem. We are given a point A. Given a point A means that we know the coordinates x and y of these points. And we are given another point B. We know the coordinates of B. It is not our task to find the location. So what's our task? Imagine that you have a wire, and this wire is flexible in your hands, but as soon as you form it in its final shape, it will take its final shape. For example, let us say that this is you will shape the wire in this shape, and you will use this wire to connect both points A and B. After shaping the wire, you will do the following. You will pass a ring or a bead, and this bead will slide down because the direction of the gravity is vertically downwards, so it will slide under its own weight from A to B. The question is, or the problem is, you do not know the actual shape of the path, the actual shape. Indeed, this path will be a function x. However, this function is unknown. Indeed, you know the coordinates of the beginning point A and the end point B, but you do not know the shape of this path. You have the freedom to find any shape. However, you have a requirement to fulfill. The requirement is that the time taken for this bead to slide from A to B should be minimum. What's the meaning of this? To clarify the following, assume that you constructed 2 paths. The first path that you have constructed is this red path. So the bead slided from here to here, and you measure the time. And since this path is in red, so you have measured the time from A to B. Measure by a clock. And then you repeated the experiment, but with another path, a straight line from A to B, and the bead also slided, and the bead also slided from A to B. Sorry, no. And the bead also slided from A to B. However, the time here will be TAB, which is in black. So the question is, which one is bigger, whether the black one or the red one? Indeed, the answer is not straightforward. Anyhow, when we can repeat this experiment infinite number of times, we can even repeat for a green path which seems like this. And we will have a new time, TAB. We have infinite values for TAB depending on the value of y of x. So we are searching for y of x for which TAB is minimum. TAB should be minimum. Somebody may feel that the problem is trivial, and he may guess that the time for the minimal path is the straight line. However, this answer is incorrect. This is wrong answer. Why? Because we are not looking for the shortest distance. A straight line will give you the shortest distance between A and B for this flat screen. However, you are not looking for the shortest distance. You are looking for the shortest time. And by the way, a straight line is incorrect, as we will see on the next lecture. So it's a tricky problem and it requires much time. So anyhow, what happened for the challenge which was issued in 1696 by John Bernoulli? That challenge was solved before January 1697 because John Bernoulli allocated 6 months for people to try to solve his puzzle. It was solved by Daniel Bernoulli. Daniel Bernoulli is the son of John Bernoulli. However, it seems that John Bernoulli did not recognize the solution of his son, or did not, he did not confess that his son solved the problem. However, also Leibniz independently solved the problem, and this was recognized by John Bernoulli and maybe others also. However, something interesting occurred. Now, on 29 January 1697, after the deadline of the contest passed, the information reached Isaac Newton in England. And at that time, indeed, information did not communicate as soon as it's at the same speed it communicates now, because there is no internet and there is no telephones. So just by coincidence, Isaac Newton received the information by a letter from somebody from France, and in fact, John Bernoulli, he resided in Germany or in the middle of Europe. I'm not sure where, but the information just flowed from France to England. And then, as soon as Newton received the challenge, he solved the problem by the next day. However, he published the work anonymously for some weird reasons, and it's not now our topic. But if you are interested, you can consult this book, Analytical Mechanics by Lewis Hand and Finch, for more explanation about this interesting story, and even for some more explanation about the theoretical details that will be described in this lecture. So anyhow, Isaac Newton described the solution anonymously. He did not write his name for the solution. However, Bernoulli, when he saw the solution of Isaac Newton, he recognized the work as Newton's. And he made a famous remark saying that one recognizes a lion from his claw marks. A lion is different from any other animal, and you can recognize him even if the lion himself is absent, just from his claw marks. So the problem is interesting, but the question is, what is the relation between this problem and variational calculus? So this takes us to the next question. What is variational calculus? What is variational calculus? What's variational calculus? So to answer this question, I would like to postpone even now some more mathematical details, and I would like to provide some more explanation about the problem posed by John Bernoulli. The problem, by the way, is termed as Brachistochrone problem. Brachistochrone problem. This problem is termed as the Brachistochrone problem. Chron stands for time, and Brachisto stands for the fast. Both are Latin words. So I would like to give more explanation about the Brachistochrone problem, how to tackle this problem or how to describe the problem. So this is the problem. We have point A and another point B, and we are searching for the path which gives us the smallest time. However, to make things even easier, let us assume that we have already some specific path, like this one, and we want to measure the time. How to measure the time for this path? Forget about getting now the minimal path. Assume that you have some path and you want to measure the time. How can you get the time? So let us revise some mechanics, and since the bead is sliding on a frictionless in a frictionless motion, then we can use the principle of conservation of energy. So let us assume that the bead now has slided in the vertical distance y. So we can apply the principle of conservation of energy between point A and the new position, whatever the name of this position. So the conservation of energy tells us the following. Let us postpone a little solution for the time. It tells us that half mva squared, which is the kinetic energy, plus mgh is the vertical distance measured from a fixed datum, which will be the end point B. So this is h. The kinetic energy plus the potential energy should be equal to half m v squared. V is the velocity at this position, plus mg. I will write h, where h stands for the vertical position from B to some specific position on the path. So this is the principle of conservation of energy. To make things even more easier without losing any generality, we will assume that VA is equal to 0, which means that the particle starts here from rest. The particle starts here from rest. So please remember that y here is the variable. You can work either in terms of y or in terms of h. If you are going to take y vertically downwards, then we should get rid of h. In fact, h small is equal to h capital minus y. So you can rewrite the information or the equation this way: mg h capital is equal to half mv squared plus mg, and instead of h small I will write uppercase h. Indeed, this term is cancelled with this term, and you can write that half mv squared is equal to mgy, or the loss in the kinetic the loss in the potential energy is gained as a gain in the kinetic energy. Potential energy is lost to kinetic energy. So indeed, you can even make more simplification and reach the familiar result that v squared, or v, is equal to the square root of 2gy. How can we translate this to time? Now we have the velocity, and by the way, the velocity is equal to ds by dt, where s is the distance measured parallel to the path or coinciding with the path. So if we take a small place or a small section here from the path and try to magnify it, if this is ds here is a very small segment which is parallel to the path. However, it is described by two infinitesimally small small displacements dx and dy. This is ds. So in fact ds can be written as square root of dx squared plus dy squared. So we have now a relation between velocity and dt. So let us go further. So v, which is equal to square root of 2gy, it's equal to the square root of dx squared plus dy squared. This was ds over dt. That's very nice. So we can have now dt on a single side. So dt is equal to the square root, a big square root of dx squared plus dy squared over 2gy. And if you want to find the time from the point A to the point B, you need to make a definite integral of dt from point A to point B, which is equal to the integral from A to B. However, now this square root, I will do some manipulation. I will take dx outside. I will take dx squared outside. Of course, when you take it outside, it will be just a dx. So we are left inside with the following. We are left inside with 1 plus dy over dx the whole square divided by the square root of 2gy, and we got dx squared outside, so we have now a dx. And indeed, if you are paying some attention, you will notice that you can write the equation in this way. So the time is equal to the integral from the point A to the point B. It's a definite integral of the square root, a big square root of 1 plus y prime squared over 2gy dx. So this is the time. Indeed, if you want to evaluate the time, you will need the specific value of y as a function in x. If you have this value, you will find y prime, which is equal to dy by dx, and you will be able to get a nice value for the time. However, as we have already mentioned, we do not know the path. We are searching for the path that will yield us the smallest time. So now, more or less, we are prepared to understand what's the meaning of variational calculus. It goes in this way. Suppose you have some integral. It's a definite integral. Of course, time plays the role of I here. Time here plays the role of I. And I can even write it here. Suppose you are having this integral, and this definite integral is a function. It's not a function, in fact, you are integrating some function f capital, and this function is a function of y and y prime and x dx, and you are performing the integration from the point x1 to the point x2. Indeed, point x1 and x2 here were xa and xb, and the function f capital, of course, is this big square root f of y and 1 prime, and x here is the square root of 1 plus y prime squared over 2gy. So this is our problem now. We are having this integral, and we know very well the limits of this integral. In other words, we know x1, we know x2, and we know the shape or the form of f capital. However, the unknown here is y of x is unknown. But we have a condition to find y of x, is that I should be an extremum. The word extremum, in fact, can be translated into two results. It's either a minimum or a maximum. Indeed, for the example of the Brachistochrone, it was a minimum. However, in other applications, it can be a maximum. So now this is the problem, or this is the basic problem of variational calculus, of calculus of variations. We want to know why. And by the way, you can sometimes you can denote I by the term functional, because I is a function in the unknown function y. You have infinite variations, or you have infinite choices for y, and for each choice you will find, for the function, you will find a single value for the functional. That's why we call it a functional. So we want the function y of x, we want the function that will make the functional an extremum, either a minimum or the maximum. So this is the basic problem of the calculus of variations. So now we understood what we have. We have the limits, we have the integrand, but what we do not have is y. We are searching for y, however we are having a condition to be satisfied, that the function should be either a minimum or a maximum. So how can we reach this? I will not answer this problem specifically or in the special case of the Brachistochrone. I will write a general treatment for any problem, and then in the next lecture I will apply the results to specific problems like the Brachistochrone or other problems. So let us go further and see what we have now. So we have I, and we have the following. Let us plot two axes, a vertical y-axis and a horizontal x-axis, and we have two endpoints, and as I have already mentioned, those endpoints, they are either A or B or whatever, they are fixed. I will denote them by 1 and 2. 1 and 2. So this is point number 1, and this is point number 2. So we are searching for a path, and as we have already mentioned, we have infinite paths. However, assume the following. Assume that you are lucky, and by some strange method, you have reached the optimal path in green. So this is the solution, and call it y star. It means that I of y star, and indeed y star prime, is extremum. Assume that you have obtained the optimal solution, and now you would like to study the behavior of the functional, or the behavior of I in the neighborhood of y star. So to study this, I will make the following. I will make a small variation. I will make a small variation in the y star. It means that I will plot, or I will examine another path. The path is very close to y star. The difference between y star and the other path is very small. The difference is very small, and this difference will be termed as delta y. So this is the difference. As you see, everywhere the difference is small. So this difference is termed as delta y. Delta y is equal to y star minus y in general. So delta y has a very important condition. It should be infinitesimal to make sure that we are in the neighborhood of the optimal solution. So what will happen to I in this time? So this is an extremum, I of y star prime. This is, however, what will happen when we evaluate I at y star plus delta y, and at y star prime plus delta y prime also. What will happen? It will be equal to the following. It will be a definite integral from 1 to 2 of f capital of y star plus delta y, comma, y star prime plus delta y prime comma x. And here we have a very important notice or observation. We do not have delta x because the values of x are fixed. The values of x are fixed. That's very important now. This integral, as I have already mentioned to you, is a definite integral between 2 points, from point 1 to point 2, and point x1 and x2 are definite and they are given. So we have a fixed interval for x1 and x2. There is no variation in x1 and x2. By the way, we call x here independent variable. Independent variable. And we call y a dependent variable. Indeed, the choice of x and y for dependent and independent seems arbitrary for the case of Brachistochrone problem somehow. However, it's not the same in other applications, so you can just accept my choice now without any problems, I think. So let us go back and to our result. So what we have reached the functional after making a small variation. By the way, don't forget that delta y itself is a function. Yes, its value is small, but we did not impose, for example, that it can be a constant. And also please remember the following, that delta y at the beginning and at the end is equal to 0. This can be written as delta y 1 or delta y of x1, which can be termed as delta y1 is equal to 0. Why? Because we do not allow any variation at the ends, because fortunately we know at this point we know very well the value of y1, and at this point we know very well the value of y2. When we return back to our problem, this integral, it's not just no x1 and x2, but also you are given x1 y1 and given x2 y2, and this was also the case for the Brachistochrone problem. We know here the values for xb yb and xa ya. So fortunately things are not so bad. So let us go now to see what we can derive. So the condition that delta y is infinitesimal can be used in some useful manner. How? I will rewrite the integral in this way. I will write I as the following. Let us differentiate I from the optimal value of the function in the following. I can be written as the following. In fact, I will write the following. The integral will be from 1 to 2. However, f will be equal to f of y star prime of x dx. Of course, now you can object because this one is not equal to this one. Yes, but I'm not finished yet. I will write the following. I write plus delta y partial f by partial y evaluated at y star plus delta y prime multiply partial f by partial y prime evaluated at y prime equal to y star prime. And this one, by the way, f is a function in multivariables, so it should be evaluated at y prime star is equal to y prime, and here y is equal to y star. So I am using here Taylor series expansion for a function in multivariables, and this function in multivariables, in elementary calculus textbooks you can find more explanation about this. However, for this expansion to be valid, we need that delta y and delta y prime should be small enough. However, I will not just stop here. I will write plus higher order terms, or I will write terms of the second order in delta y. So now, up to now, this is the exact equality, because I did not neglect anything. Even the terms of order delta y is still there. Delta y squared is still there. So what did we gain now? The gain will be the following. The gain will be the following. In order, I will write this in nice. In order for the functional I to be extremum, the first order dependence on d delta y. I'm sorry, I cannot write Greek. Must vanish. What's the meaning? The meaning is that if we return back to the last slide, those terms partial f by partial y and partial f by partial y prime are first order terms in delta y, as we will see later. So in order for I to be extremum, these first order terms must vanish. Okay, so what's the reason for this? If you are familiar with calculus of a single variable, we have something similar here. Suppose, let us forget a little bit now that I is a function, or I is a functional. Assume that I is an ordinary function now. Assume for a moment that I is not a functional, but it is an ordinary function, and forget that y is a function. Assume that y is an ordinary variable. So for the functional to be either a minimum or a maximum, we have here the condition that its first order derivative must vanish, or it will have the tangent must be horizontal. Of course, here it means that partial r by partial I by partial y should be a 0, either here or here, either at this place or this place. So it is easy to, indeed this means that the first order dependence of I on y vanishes. It's very easy to visualize this condition for a function of a single variable, but for calculus of variation, the visualization is very difficult. So we can argue, but in a different matter. Assume the following, and I'm taking this formal proof also from the book of Hand and Finch. The formal proof I'm going to present now is also found in the book of Hand and Finch. The proof is the following. Assume that you know I star. Assume that you know I star. Assume that you know I star now, and you are trying to, it's given. Assume that you are just known and you are happy now. And assume that you are studying the behavior in the neighborhood of I star. So let us assume further that you know that I star is a minimum. And then you did the following. You try to evaluate I. If you know I star, then indeed you know Y star. So you evaluated I at Y star plus delta Y. Is it possible that this, let us call it I1. Is it possible that I1 to be smaller than I star? The answer is it's impossible. You can never find I1 smaller than I star, because I star is the minimum. So this is impossible. However, it may be possible that I1, or it is possible that I1, or indeed that will be the case, since it's I star is the minimum, then I1 will be bigger than I star. That's very nice. So I1 which occurred when we plugged delta y is bigger than I star. Suppose we reverse the case. It means that by reversion I mean that I will evaluate I2, which is evaluated at y star minus delta y. Minus delta y. If the first order effect exists, then the effect here of delta y was increasing I1. If the effect of delta y is first order, then the effect of minus delta y would be decreasing I1. And if I1 decreases other than I star, we will have this impossible situation. So to get rid of this impossible situation, we just conclude that first order dependence must vanish. Of course, it's proven. I have investigated the case where I star is the minimum, but you can reach the same results working with I star a maximum. So, in other words, let's assume that I is equal to the following: it's equal to I star plus some coefficient multiply delta y plus high order term. Unless this coefficient vanishes, then for a positive value of delta y, you will have I bigger. Let us assume that this coefficient is positive now. Assume that the coefficient is positive. Then for a positive delta y, I1 of a positive delta y will be bigger than I star. This is possible if I star is the minimum. However, if you put I1 of negative delta y, you will get, I2, you will get something smaller than I star, and this contradicts with the assumption that I star is the minimum. That's all. So to solve this dilemma, this coefficient must be equal to 0. So now we know what the condition we have for reaching an extremum. The condition is that this term should vanish. It's an integral, by the way. So let us return back. So the first order term must be equal to 0. What's the first order term? It's a different integral between 2 points 1 and 2. The first one is partial f by partial y, and the second one is variation, also y prime, partial f by partial y prime. The both of terms are integrated with respect to dx. Excuse me now. Let us focus on the second term, and let us rewrite it here. The second term is equal to partial f by partial y prime, and variation of y prime, it is variation of dy by dx. The variation itself can be regarded as an operator. So you can exchange the order. You can exchange the order of these two operators, the total derivative and the variation. Partial f partial y prime is untouched. Please don't forget that this is a different integral. And I will write d by dx of delta y. Now, people familiar with integration will think that we can use or may suggest using the method of integration by parts. The method of integration by parts, you can find it in any standard textbook, tells you that if you have a function u multiplied by a perfectly differentiated function dv, this integral can be written in this form. It will be u multiply v minus v du. So who plays the role of u here? It's partial f partial y prime. Who plays the role of dv? It is this term. this is dv. So easily you can write u multiply v. U, it is partial f by partial y prime evaluated multiplied by delta y. This is the perfect integration. But please don't forget that this is at a definite integral, so you have to substitute by the upper and lower limits, and it's not a plus, sorry, it's a minus, the minus sign here. Think that this is very clear. Integral from 1 to 2, and v, as we have already mentioned, is delta y. But please don't forget that you need to find du. Du is the differentiation of u. U is partial f by partial y prime, so we need to write d by dx of partial f by partial y prime integral with respect to dx. Now, if we examine carefully this term, we will be so happy to observe that it's equal to 0, because this term can be written as partial f by partial y prime evaluated at point 2 multiply delta y2 minus partial f by partial y prime evaluated at point 1 multiply delta y1. And let me remind you that among the conditions we have imposed on the variation is that delta y1 and delta y2 must be equal to 0. Delta y1 here and the delta y2 must be equal to 0, because yes, we do not know the value of the variation at the middle, but we are sure that there is no variation at the 2 points at the end and the beginning. We have to use our information efficiently. Yes, and we have, yes, we know delta y1 and delta y2 at the edges, but we made use of this very small piece of information efficiently, as we have seen. So perfect. Now so this term, which term? This term now have been simplified or transformed to this term, and please observe that we have here coefficient delta y and we have here coefficient delta y. So the first order term can be rewritten as 0 equal to integration from 1 to 2 of delta y, it's a common factor, partial f by partial y minus d by dx of partial f by partial y prime, the whole integrated with respect to dx. So the condition now is that this term must be equal to 0. This term must be equal, the integral must be equal to 0. You will feel a little bit lost because we are still left with an integral which is very vague, unclear. However, this is not the case. Why? Please remember that delta y, which is a function in x, can take infinite number of values. Infinite number of values. In other words, delta y, yes, it is infinitesimal, but it is arbitrary. Arbitrary. It can take infinite number of values. So this integrand now consists of two parts. The first part is arbitrary. Arbitrary means what? It can take many values. It means that this delta y it's impossible to make it responsible for this 0. Yes, if it is 0, if it takes by coincidence the value of 0, which is a single value from many values it can take, then this will be 0. Yes, but this does not solve our riddle, because always this value, always this integral will be a 0. So to find a sufficient condition for this integrand to be at 0, you cannot impose your condition on delta y, because it's arbitrary. You cannot fix it. You have to impose your condition on this term. You have to impose your condition on this term. So simply you will write that partial f, this is the condition to be fulfilled, partial f by partial y minus d by dx of partial f by partial y prime is equal to 0. That's very nice. Now we have transformed our integral constraint. The constraint on I was an integral one. We had a constraint that I should be minimum, yes, but this constraint was an integral constraint, and dealing with integral equations in general is not easy. It's not easy. So we have an integration, yes, we have the constraint is minimum, yes, but we don't know why. However, we have reached this new condition. This new condition, this one, which is termed as, I will write it in clear letters because it deserves so. This is Euler. It's a very famous equation, Euler-Lagrange's equation. Euler-Lagrange's equation. It's a differential equation. This is an ordinary differential equation. In fact, if you examine the term carefully, and this is an ordinary differential. Indeed, ordinary differential equations are not easy, I agree with you, but they are easier than integral equations. So, for the case of the Brachistochrone problem, we had f is equal to the square root of 1 plus y prime squared over 2gy. So the dependence on y is clear, and the dependence on y prime is clear. Indeed, you can get the term partial f by partial y. You can differentiate this and differentiate this with respect to y prime, and you will write a long differential equation and solve it. So the equation now, it's just a matter now of some lengthy calculus. So that's what I'm going to explain on the next lectures, dealing with more examples about calculus of variation. And thank you very much.